Hey guys, Mrs. Dan's here. So we're on lesson 2 in our Pythagorean Theorem unit. So yesterday we learned that the Pythagorean Theorem will find the missing side of any right triangle. The Pythagorean Theorem is a squared plus b squared equals c squared. Well, now we're going to kind of go in reverse. I will give you 3 sides of a triangle and you will determine whether it's a right triangle or not. So that's why it's called the converse of the Pythagorean theorem. So if 3 numbers work in the Pythagorean theorem, that must mean those 3 numbers are the sides of a right triangle. So make sure you have a calculator, copy the objective, and do the do now on the top of page 5, and I'll go over it with you in a few minutes. So in the directions, it clearly says that both of these answers will be rational numbers, so I don't have to worry about rounding. To find the missing side of a right triangle, we could use the Pythagorean theorem, a squared plus b squared equals c squared. Remember that a and b are called the legs. C is always across on the right angle, and that's called the hypotenuse. So I'll do 16 squared plus 12 squared equals c squared. When the numbers are a little larger like this, I do like to use my calculator. So 16 squared is 256. 12 squared is 144. And when I add 256 to 144, I think I get 400. I'm going to double check myself. Yep. And then we have to do the square root of 400, which is 20. I am going to show my work though. I will square root both sides because the square root crosses out the square. All numbers have 2 square roots, so the answer to the equation is positive or negative 20, but the answer to the question is only 20 because the length of a side of a triangle can only be positive. And in letter B, remember that sometimes it's an equation using inverse operations that I have to solve because look, they gave me C. So I'll call this A and B. Again, it doesn't matter which is your A, which is your B, but your C is super important. So I'm going to substitute a 10 in for B. 10 squared is 100. 26 squared is 676. I subtract 100 from both sides because I'm trying to isolate the variable. And then I take the square root of both sides, and they did tell me in the directions that both answers are rational, therefore there is a square root of 576. I honestly don't know what it is off the top of my head. Square root of 576 is 24. It is positive or negative 24 to begin with, but the final answer, since it's a side of a triangle, is just positive. It is okay that you don't write both the positive and negative when you're doing Pythagorean theorem, but you do have to write it when you're just doing a normal math equation. So this is just a summary of what we did yesterday, that it's for right triangles, and A and B are the legs, C is the hypotenuse, and we can do a squared plus b squared equals c squared. Well, the converse is also true. So if the lengths of 3 sides of a triangle are A, B, and C, first of all, C is always along the side. The hypotenuse is always the longest. So when they give you 3 numbers, the largest number is automatically your C. And then we kind of test it in the Pythagorean theorem to see if it works. If it does work, then we say, yep, it was a right triangle. If it doesn't work, then we say, nope, it wasn't a right triangle. We'll talk about these when we get to the next page. So in exercise 1, they give us 3 numbers, and they're asking, could they be the sides of a right triangle? And we have to justify using the converse of the Pythagorean theorem. So to justify really means show or work. So first of all, you look at all 3 numbers, you find the largest number and you call it C. It's not always the last number in the list. In all 3 of these cases, it happens to be the last number in the list, like 29 is the largest out of all 3 of these. 39 is the largest out of all 3 of these, but please know it doesn't have to be in order from least to greatest. And the largest number is what the C would be, because the hypotenuse is always longer than its legs. But not all of these will work. Not all of these are right triangles. So we start with a squared plus b squared equals c squared, and we substitute in the numbers is 28 squared plus 45 squared equal to 53 squared. And that's actually a question. I don't know if it's true, so I'm putting a question mark there. And now I'm going to use my calculator. I'm going to show you that on the calculator, you're actually allowed to enter all of this at once and just write down the answer. You don't have to do 28 squared, write it down, 45 squared, write it down. You could do this, 28 squared plus 45 squared, and then just write that underneath the 2. So 2,809, 2809. And I'm still checking to see if it's equal to 53 squared. So if we use our calculator and do 53 squared, we get the same answer. So what I do is I put a check here, and then I say, yes, this is a right triangle. Because the question is, could it be? So the answer has to be yes or no. Letter B, we'll do 17 squared plus 22 squared equals 29 squared, and then I pick up the calculator. Pythagorean theorem really shouldn't take a long time. It's a lot of calculator use. I need you to get used to using your calculator. All right, so it didn't turn out to be equal. So 773 does not equal 841, so I put a slash through that equal sign because it's not true, and I say not a right triangle. Okay? Because we're determining if it's a right triangle or not. Why don't you try C, and then you can check your answers with me. Someone can hit pause while you're doing it. So you can see I wrote down 15 squared plus 36 squared with a question mark. Does it equal 39 squared? And then over here on my calculator, 15 squared plus 36 squared is 1521. And 39 squared is also 1521. So check that it worked out, which means we say yes, this is a right triangle. So you can see that some sets of numbers do create a right triangle, other sets of numbers do not. Not all triangles are right, so it makes sense that not all 3 numbers always work. So there's a special thing about when you do the Pythagorean theorem, if the sides of the triangle turn out to be whole numbers, we call it a Pythagorean triple. So over here, 16, 12, and 20 in our do now, since they were all whole numbers, that's actually a Pythagorean triple. And letter B of the do now was also a Pythagorean triple, 10, 24, 26. It's actually hard to find 3 whole numbers that work in the Pythagorean theorem, because so many times when you take the square root of a number, it's actually irrational, right? We saw that yesterday. So When we get whole numbers, that's when we say, ah, that's nice. Let's call it a Pythagorean triple. And the most famous Pythagorean triple is this 3, 4, 5. We call it a 3, 4, 5 right triangle. This is famous. It's like so famous that construction workers actually use it when they're trying to build buildings, or build anything where we need right angles. They're creating triangles along whatever they're building and making one side 3 feet long, let's say, another side 4 feet long, and then making sure that the hypotenuse of 5 feet long fits in there. When I see you in person, I could show you what I mean, but they adjust, like maybe a wall that's standing up. If it's slightly on a slant, then that hypotenuse of 5 won't fit in there, so they have to like swing the wall out or swing the wall in so that they make a right triangle. So honestly, it's used often when building things that we need right triangles for. But in exercise 2, we have to justify that whether something is a Pythagorean triple or not. I know 3, 4, 5 is a Pythagorean triple because it's so famous, but we're going to prove it. So how do you prove it? Use the Pythagorean theorem. Show that 3 squared plus 4 squared actually equals 5 squared. These numbers are so small, I'm not even picking up my calculator. I'm just going to do 9 plus 16, which turns out to be 25. And guess what 5 squared is? It's also 25, right? So 3, 4, 5 is the most famous one because actually it's the only 3 consecutive whole numbers that work in the Pythagorean theorem. 3, 4, 5, right? They're consecutive. There's no other consecutive numbers that will work in the Pythagorean theorem. So let's do letter B, see if it is a Pythagorean triple. Is 14 squared plus 22 squared equal to 30 squared? This is just like what we did before. We'll use our calculator. So you can see on my calculator that 14 squared plus 22 squared is 680, but 30 squared is 900. So 680 does not equal 900, therefore this is not a Pythagorean triple. Going forward from now on, I'm just going to say yes if it is a Pythagorean triple or no if it's not. I don't want to write a whole sentence, and it's not necessary to. It doesn't say explain, right? Letter C. Does 5 squared plus 12 squared equal 13 squared? You can hit pause and do it yourself and tell me yes or no. Hopefully you got yes. Right? It turns out to be 169 equals 169. Why don't you try D, E, and F also? You're just doing A squared plus B squared equals C squared. So for D, I got yes. 5,329 equals 5,329. Honestly, just looking at the 3 numbers, if it's not a famous triple, I don't know if it's going to work or not. I actually have to do it. So letter E also turned out to be yes, because each side turns out to be 900. And letter F is not a Pythagorean triple. Both sides didn't turn out to be the same. So exercise 3 talks about the most common Pythagorean triple, which is the 3, 4, 5. I told you it's the only 3 consecutive integers that work in the Pythagorean theorem. But something that's so great about remembering 3, 4, 5 is that any multiples of a 3, 4, 5 right triangle also are a Pythagorean triple. And what I mean by multiples, take a look at letter A here. Right? Do you notice that if I think about a 3, 4, 5 right triangle, And if I use a factor of 2, if I multiply this by 2, multiply this by 2, and multiply this by 2, I actually get 6, 8, 10, right? I get these three numbers that are here. So multiples of any Pythagorean triple will also be a Pythagorean triple, because when you're multiplying all three numbers, it's like doing a dilation, right? Remember, we can multiply all sides of a figure by the same number, which is called the scale factor, and it creates similar figures. So if this is a 3, 4, 5, if I multiply everything by 2, then this could be a 6, 8, 10. If this is a right triangle, then its dilation must also be a right triangle, because remember, dilations make similar figures. Similar figures mean same shape, just a different size. So the shape is the right triangle. The size is the lengths of the sides got bigger. And we can prove it. If you really don't believe me, I could do 6 squared plus 8 squared and show you it really equals 10 squared. So 36 plus 64 is 100, and 10 squared is 100. So really, the 6, 8, 10 is also a Pythagorean triple. So if it's a multiple of a 3, 4, 5, then it is a Pythagorean triple. So letter B is a Pythagorean triple. It is a multiple of a 3, 4, 5. My question is, what is that scale factor? What do you multiply 3, 4, and 5 by in order to get 9, 12, 15? You're right. The scale factor would be 3. So the 9, 12, 15 is also a Pythagorean triple. Now on your test, I'm not going to ask you really to find like what the scale factor is, what could you multiply each thing by, to make a new Pythagorean triple, but I will give you a Pythagorean triple, and I will give you 3 sets of numbers, I should say, and I will ask you, is it a Pythagorean triple? So if you notice it's a multiple of a 3, 4, 5, then you could just say, yep, it's a Pythagorean triple, because if you multiply a 3, 4, 5 triangle by 3, then you get a 9, 12, 15. If you don't notice that, then you just do the Pythagorean theorem. You just do the 9 squared plus the 12 squared and prove to me that it equals 15 squared. That's what a lot of you will probably do, because you don't always notice right away if it's a multiple of a 3, 4, 5. I notice it more than you, but that's because I've been practicing more than you. So if you get yourself into a habit of like stopping and looking, maybe you'll be able to see if it's a multiple of a 3, 4, 5. But if not, then you just do the work. You just do the Pythagorean theorem. This I can easily see it's a multiple. What do we multiply by? Yeah, it's 11. Multiply by 11, or the scale factor is 11. So it is a triple. Okay? And this last problem, and then you get to start your homework. So remember, we talked yesterday about squares and rectangles and drawing the diagonal, and you make a right triangle. So we have to draw and find the length of a diagonal in this rectangle shown. So here's the diagonal. The length, remember, since it's across from the right angle, is side C. So let's do 16 squared plus 28 squared and find out what C squared is. And notice in the directions, I already know I'm going to have to round. So 16 squared is 256. 28 squared is 784. when I add 256 and 784, my wrong buttons here, 256 plus 784, I get 1040. Remember, we're not done now. That's what c squared is. So now you square root each side, because the square root crosses out the square. The square root of 1040 rounded to the nearest tenth would be 32.2. I'm changing this to a squiggly equal sign. I don't like equal signs when I round because it's not equal to that, it's about that. And if I use my units, I say that the diagonal is 32.2 centimeters. And that's it. Still just Pythagorean theorem. It's just that I can give you 3 numbers and then you just test it out in the Pythagorean theorem. If I ask you if something's a Pythagorean triple, really it's still just testing out to see if it works in the Pythagorean theorem. Every once in a while you'll be able to notice that it's a multiple of a 3, 4, 5. But looking at all these, maybe some of them are multiples, maybe some of them are not, maybe you're uncertain, so just use a squared plus b squared equals c squared to guarantee getting a right answer. You can start your homework, and I'll see you soon. Bye.